So welcome everyone to the latest September 21st. Happy fall, everyone. Well, yeah, if you're in the Northern Hemisphere, Southern Hemisphere, happy spring. um, thank you for being here at this, and I apologize again that I didn't get the reminder out until I did send one yesterday, I believe, but I usually get it out an hour beforehand to the day of, but lost track of time for a little bit. So this is the Trees Around the Globe Student Research Campaign webinar, and we will be focusing on a celebration of land cover and tree height observations from the ground in space, where we're going to, Peter Nelson, who's going to be talking, very in detail about the legacy of Landsat 9 missions with NASA and USGS, as well as the upcoming Landsat 9 launch. If everything would have been to schedule, Landsat 9 would have launched last week on the 16th of September, but that did not happen. So right now it has been pushed off to sometime between the 27th and the 29th of September. So that's what we're hoping for right now. So we're going to take a deeper dive into some of the missions that will play a vital role in any upcoming things that we do with the campaign. Looking at Landsat, of course, ICESat-2, GEDI, GPM, and ECOSTRESS missions. Now, I also want to mention that we are awaiting the final approval for the Trees campaign extension. It's looking really good. So we're just waiting to hear from GIO. They're getting everything together with the Trees campaign and Mission Mosquito and the service temperature field campaign as well. So they have a lot of things going on their plate right now. So we will hear shortly, and once I hear any information on that, we will continue. But thank you everyone for your support and your willingness to provide testimonials why we should continue this campaign. So that's highly appreciative. We use some of your quotes, that you've sent me, or you you said during one of the webinars in the past, as part of our, campaign extension request with GIO and NASA. So let's get started. Oh, I should also mention, if everyone would, keep Sequoia National Park in their thoughts. Right now, there's a wildfire raging there, which potentially threatens basically the giant sequoias in that area. They've took a lot of precautions, like wrapping a lot of the trees, like the General Sherman tree, which I highlighted, I believe was last webinar, the 275-foot General Sherman giant sequoia. So the giant sequoia forest there is, threatened right now. So they've done a lot, as I mentioned, a lot of precautions, wrapping them with, some fireproof things and some spraying as well. So, and the park's closed. So, keep that in your mind, because it's literally, the fire has reached part of that giant sequoia area. So it's knocking right on their doorstep right now. So, keep that in your thoughts. There's due primarily, there's several fires going on there, but due primarily to lightning strikes in the area. So, and we all know that, with the increased storms and everything, that's a result of a changing climate. So, please keep Sequoia in your thoughts, because, it would be devastating to lose any of these trees. It's such a rich part of, history of the United States, California, and the world, these trees. So with that said, let me continue. I decided to, as I usually do, focus a little bit on, highlighting a tree. It's an El Arbol de Tule. And you can see here, pronounced Oaxaca, okay, in Mexico. And I put that there because a lot of people might not know how to pronounce that. But this is the tree of Tule, famous for its structures. You can see here the base of this is just massive. The canopy is massive too, but if you look at this, the base is massive. At the tree's trunk is about 46.1 feet or 14.05 meters in diameter. Okay, and the circumference, that translates to 137.8 feet or 42 meters in circumference, and it's approximately 111 feet tall. So it's one of the oldest and most expansive trees in the world, and it's located in Mexico. I don't know if anyone has ever, seen this in person, but it looks like in this photo, it's in an area, area that has a little bit of a population. So a lot of people may have seen this, and as you can see, there's lots of tourists in these photos. But I just like to showcase, just some weird, wild, and wacky tree photo, tree from around the world. We've gone all over and looked for these crazy trees. So, and I know a lot of you like doing that ever since we had our speaker from South Africa and the baobab trees, which are just one of my favorites to see. and look at. I'd love to see those in person someday. So today webinar, here is the agenda. We have, once again, I'm going through the introduction. We'll show some metrics, and then I will showcase the Landsat 9 video, and then we will jump right in then to Peter Nelson talking about, the Landsat 9 mission, the Landsat series of satellites, why they're important for, the observations that NASA takes, and why they're super important for what we do as part of the campaign, and everyone taking globe observations through the app and through the website, just taking these observations of land cover and tree height and things like that. So a couple of things, videos that Peter's going to focus on, and some online tools that Peter will bring forth to everyone and discuss. And then we're going to dive deeper, as I mentioned earlier, into some of the missions. We talked a little bit about these in our breakout sessions, the last two webinars, but we wanted to go in a little deeper because these really serve as a really important way to compare some of this ground-based data that your students and yourself and citizen scientists that you may know of are taking, out on the ground. Since GLOBE is a NASA-funded program with support from NOAA, NSF, and the U.S. State Department, we really want to do a lot with these missions, and we've been putting those into a lot of our webinars, from the beginning, because we started the campaign, exactly when the ICESat-2 satellite launched in 2018, and more to that in a second. But we really want to focus on, how relevant these missions are to, our goals and objectives for this campaign, and, our hopeful continuation of the campaign, because, these missions are up there taking measurements 24/7. And we have measurements coming in from the GLOBE program, basically 24/7 across the world. So they go great hand in hand. The science, the technology, everything goes hand in hand. And then we're going to have a couple of things here as part of an informal discussion towards the end of the webinar after we talk about these missions. And we have a couple poll questions here. I'm going to pop up in a little while, and then we're going to pose a question. Well, also, sorry, before that, ask us anything about, what you want to learn about or hear about in the, upcoming, continuation of the campaign. And then also there's a question here I want you to think about while you're listening to everyone. And our team came up with this. It's an open-ended question, and it's, do you think like a tree? And I want people to think about that, and we're going to discuss this a little later. We don't have specific answers to this, but we thought about this because we want you to let us know, what do you think it means to think like a tree? Okay, it sounds strange, but it can bring some great discussion, and hopefully it will towards the end of the webinar. And then we'll finish off with that and any last minute things that we want to talk about. So once again, here's our core campaign team. I won't go through this anymore. I always pop this up here. Here we have the active participation for this Trees Around the Globe student research campaign. As you can see, we have participation from all over the world, and this is great, isn't it? All these countries that you see highlighted in green have been active in the last 3 years. And what that means is active. That means a combination of coming to the webinar as educators, bringing students to the webinars, taking observations, creating IVSS projects aligned to the campaign, and then participating in any other, part of the campaign, in general. So these are there's approximately, I think it's 58 countries now that are part of it. So we're super excited to have all of you here. So with the campaign metrics, I'm going to once again pull you down to the towards the bottom where it says full campaign. Since September 15, 2018, we have over 39,000 tree height measurements from over 16,500 global sites, 23,200 plus land cover measurements from almost 16,000 global sites. And primarily thank you to the European Phenology Campaign, we have over 22,700 green up, green down, or greening observations and measurements from students from 625 global sites. And then if you compare that all the way to full globe, which is really cool because, as you can see, since the campaign started just 3 years ago, we have almost 40,000 tree height measurements. But if you go back to April 22nd, 1995, when GLOBE began, we have 52,912 tree height measurements. So you can see that since our campaign started, our campaign members and basically the discussion of the need for tree height observations, bringing out the trees tool on the NASA Global Observer app for citizen science, we've increased those numbers, the rate that those numbers come in exponentially. The entire, since 1995, 52,912. And since the campaign started, only last 3 years, almost 40,000. So there's just over 12,000 observations taken prior from 1995 to 2018, September 15, 2018. So thank you all for all these observations that are coming in. We do know that a lot of them come in from the citizen scientists, but that's been a push of ours to get this data out there. So with that said, let me go to the next one. So here's where everything's coming from. This is over the last 3 years. This is where all the observations are coming from. And this is a combination of tree height, land cover, and greenings. I'm going to mention this again. The Globe Trees Family Guide is still up there for you to take a look at if you want to have your students or people in your family take a look at and learn more about trees and land cover and get a little more advanced knowledge through activity and learning experiences. You can go through this, and it's separated into saplings, seedlings, and sprouts. Saplings are the oldest people. These are the high school through adult. The seedlings are the upper elementary through middle school, and the sprouts are for very young children up through early elementary school. So you can see when you build up from sprout to seedling to sapling, the activities get a little more advanced as science gets a little more complicated. So, and then we actually have, analyzing the data that you take in this sapling science journey section. So there's a URL on the bottom where you can just go onto Google and just type in NASA Global Observer Trees Family Guide, and it'll pop up. It'll be the first one to pop up. All right. So about upcoming NASA missions and programs, we're going to start off with Landsat with Peter, ICESat 2 and GEDI with me, ECOSTRESS with, oh, sorry, Peter. I had 2 Peters there. That should be P-E-T-E-R. Maybe it defaulted to that. I'm sorry, Peter Falcon. Sorry about that.
No worries.
That's weird. I don't know why I didn't catch that, but okay. Maybe it's just the stress of writing ECOSTRESS all in capitals. And then GPM with Dorian. And like I said, we're going to take a deeper dive into this. So what I'm going to do now is before we pass it over to Peter Nelson with Landsat and land cover and all that great stuff, and he's going to be the the backbone of what we're going to talk about, because since we're talking about Landsat 9 launching very shortly hopefully in the next 7 to 9 days, well, 6 to 8 days. We wanted to focus a lot on that because a lot of what you see and what you do with this campaign has to do with land cover. And as you know, trees are land cover. All right, so we're going to focus on that. So I'm going to start off first with this short video about Landsat, and then I will pass it over to Peter.
From 438 miles above Earth's surface, the newest Landsat satellite will collect data so detailed it can detect both natural and human-caused changes to the landscape. But what really makes Landsat unique is the half-century of data, an unbroken chain of observations over 5 decades. Let's take a look at how we got here. 1966, the U.S. Geological Survey proposes a satellite to study Earth's land masses. NASA gets the green light to build an Earth Resources Technology satellite, an experiment to study and monitor our planet's land surface from space. Launched in '72, this was the first digital data of Earth, repeated at regular intervals with geometric fidelity to allow comparison between observations. This changed how we drew maps, tabulated agricultural production, and assessed damage after disasters. In 1975, NASA launched a second satellite similar to the first. Now they were collecting twice as much data. With Landsat 3 replacing the aging original in '78, focus shifted to the advanced technology planned for the '80s. The thematic mapper instrument, launched on Landsat 4 in 1982 and on its twin Landsat 5 in '84, was a major step forward, collecting 7 different wavelengths at better ground resolution and with higher precision. This was the beating heart of the satellite and became the workhorse for a generation of scientists. For the first time, Landsat data had 3 visible bands, red, green, and blue, allowing natural color composite images. With the addition of shortwave infrared wavelengths, the data could better highlight flooded areas, mineral deposits, and burn scars from wildfires. The thermal bands were also upgraded, allowing individual farm fields to be tracked. The sixth Landsat was intended to be another big step forward, but it never reached orbit after launch in 1993. Plans immediately began for Landsat 7, which would carry an even more improved sensor. At the time, the Enhanced Thematic Mapper Plus was the most stable Earth observation instrument ever sent into orbit, and the calibration could be updated while in space. For the first time, we had an instrument robust enough to collect lots of data, and we had a plan to thoroughly record the entire globe. Landsat 7 was put to work mapping coral reefs, and even produced the first high-resolution natural color map of remote Antarctica. Improvements to the thermal bands on Landsat 7 allowed states and counties to gauge how much water was used by crops. This helps them manage water resources efficiently. An important milestone occurred in 2008, when the USGS made the data available to download for free. Users were able to get the data they needed, and not just what they could afford. It really unlocked a ton of innovation and created about $2 billion a year in economic benefits. The modern era of Landsat observations began with the launch of Landsat 8 in 2013. Having a push broom style sensor on Landsat 8 was a big improvement over the older scanning sensor. The Landsat 8 ground system that USGS runs is capable of receiving a lot more data than before. We're downloading over 725 scenes each day. That just wasn't remotely possible until Landsat 8. The two European Sentinel-2 satellites were designed to mesh with Landsat so that users can treat data from all the satellites as if it came from one single source. Now we get observations every 2 or 3 days instead of every 2 weeks. 2021 is the launch of Landsat 9, the next step forward. It will collect the best data ever recorded by a Landsat satellite, while still integrating seamlessly with the extensive archive. Since the early 1970s, Landsat satellites have allowed us to better manage our resources. Landsat data has enabled countless innovations and will let us track the effects of climate change into the future.
All right, I hope you learned a little bit about the Landsat, series of satellites, and it has a rich history in, the advancement of technology, understanding our planet's land cover. And with that, I will stop sharing and I will pass it over to you, Peter Nelson.
Well, thanks for that, Brian. I really appreciate you kind of giving this nice introduction to one of my passions, which is this Landsat satellite system that has not only been developed but maintained and allowed us to have insights that have just not been possible before this. And I think that's one of those pieces that I really want to leave you guys with today, is recognizing where we are in human history. Not only that we are, part of and able to contribute to NASA and the science that NASA and NOAA and the National Science Foundation in particular are helping to support through the GLOBE program here. It's I think pretty incredible to be part of a program here like the GLOBE program that has been going for 25 years strong. We're now award winning as well with recently this recognition from the American Geophysical Union that recently came to the GLOBE program. And I think it's important to recognize that one of the reasons for the GLOBE program is to actually help complement and make use of the Landsat series of satellites. And so, there's really a lot to celebrate right now around the GLOBE program. And so I really want you guys to kind of revel in this time that we're in right now, and the new science that is actually going to happen over the next 5 to 10 years. And that not only are you a part of, but also we can help to foster that next generation to really understand and take advantage of all of this data that has been collected by the people before us. And to me, this is a really important piece of our science endeavor here, which is actually not just making observations, but then storing them and archiving them in a location that other people can use. And that is part of what the Landsat program represents, which is this continuous Earth observations that allows us to even go back and look at places where we hadn't considered certain problems before or certain situations before. And so, that's part of what I hope you are going to explore this upcoming year, and maybe, recognize that even one observation on the ground can help us to understand the past and to help us to maybe make some predictions about the future. But it all comes back to making that observation. And one of the things in that video that was pointed out, it was how the data being collected has changed over time as technology has changed. We've learned from the past. And this is something that NASA's really, really good at. When they first put that satellite up there, there really was this kind of mission of putting it up there, seeing what we could collect, but not necessarily thinking about continuously collecting data for 50 years. That was a hope, a dream maybe, but how do you keep a program like that going? You have to have the public support, because this is a taxpayer funded initiative, which is also what makes Landsat really, really unique. And one reason why I feel very passionate about this project and about the Landsat mission is that it's public data. This wasn't true when Globe first started, and that was actually an impediment to all of our education and what we wanted to do. Here we are, 25 years later, the data is free. And so now let's turn and kind of think about the type of questions that we can answer using this type of technology, these types of observations. And you'll see behind me, I actually have a Landsat image from an area here in the western part of the United States, in Oregon, where I'm located. And you can actually see the variety of colors that are on this image. And one of the first things that humans are really good at is trying to understand these colors and the patterns that are there. And so, so if you spend a little bit of time just starting to look at these satellite images, you can walk away with an understanding of something. Now, this is where the GLOBE program comes in. These images aren't just images, they're tied to locations on Earth. And so we can actually go to these pixels. We can make measurements on the ground. And that's where the land cover, or the GLOBE site definition, really comes from, is trying to describe 9 Landsat pixels. And that gives us that 100 meter by 100 meter area. And the size of what the satellite can actually see relates to that altitude that the satellite is at. And so, these are some considerations to keep in mind, because as we talk about some of the other NASA satellite missions, they have all been informed by Landsat, the Landsat mission. Not only where in altitude should we put some of these things, but also what are the instruments that should be put on a satellite, on that Earth observation system that is orbiting Earth. And we've learned a lot about this. In particular, how do we actually share data from one country or one part of the world with another part of the world? So, there's a lot that we can actually get into with this. And so I want to give you guys just some resources and some things to consider with this. But first, before I dive into this, I'm curious, just with either a show of hands or a note in the chat, how many people have used the GLOBE exercises or lessons that use the Landsat data? How many people have actually gone through and are using the Landsat data and those exercises and lessons that GLOBE has created over the last 25 years? And if we can just kind of see either a show of hands or let us know in the chat if you're actually using those. That's really informative to us to see, because I know one of the challenges is the technology has changed. And so using the multi-spec software that was initially built around that might be a limitation now. And so there's some things like that, that if you could let us know if you are using this, that's really, really useful for us in our planning. And so I love this and appreciate it. All everything that we're doing here together. And so I wanted to help you guys recognize, because we use this word digital image a lot, but really we're making measurements across the electromagnetic spectrum. And you heard that in that video, that when we put the first Landsat satellite up, also known as ERTS at the time, it actually had just a black and white camera on it to take those measurements in those wavelengths. And then it also had some infrared bands that it was actually measuring. And that was specifically to help us discriminate vegetation versus not vegetation, forest versus agricultural areas. And we can see that when we look at a satellite image, if we bring in this near infrared or the infrared part of the electromagnetic spectrum, we can actually distinguish between the forests, which are kind of this darker green, from the agricultural areas and the grasses, which are more in this bright green. Now, remember, we're making these measurements in things that our eyes can't see. So this is the power and kind of the magical seeing that satellite data brings to us. And so, to me, this is a really important component to effectively using satellite imagery. We can do a lot with just the visible part of the spectrum, the red, green, blue that our eyes see, but we really get a lot more insights when we bring in the electromagnetic spectrum measurements beyond what our eyes see. And this is kind of the evolving part of the Landsat program. Is we've learned, we've practiced, and we figured out that we need this higher discrimination power. So you'll see that if you start looking at other satellites, say, the MODIS satellite or the MODIS instrument on the Terra and Aqua satellites, it has very similar measurement capabilities as Landsat, but it also has improved in some places. So pay attention to this. This is a really important piece, and I'm highlighting this tour of the electromagnetic spectrum because it has ready-to-use videos and a nice, helpful way for you to guide students or have students or you yourself better understand the satellite images that NASA is providing and making measurements to you. So I really highly recommend this is a great place to start when we start talking about Earth observations and measuring from space. I want to highlight this globe activity called Odyssey of the Eyes that, again, kind of walks you through understanding that satellite perspective, what we see, what we don't see. And the neat thing is, if you do this sort of exercise, you actually can develop a three-dimensional model using the actual measurements or using some of those globe measurements that you have. Especially now with that tree height tool, you can make a more accurate representation of your area and even simulate that satellite. What does it look like? What can it do? So I just wanted to remind everybody about this particular learning activity because it helps us to get into understanding this relationship between what we see on the ground and then what we are actually measuring from space. And scale is a really important piece of that. I wanted to highlight, and I'll drop this into the video, into the chat. This link, because here's a 1973 video, very similar to the one that Brian just showed us. It's 27 minutes long, so I didn't want to show the whole thing. But what's incredible about it is that in many ways, the questions that we're asking and we're trying to use the satellite image and data to answer are the same. Where are resources across Earth? What's the quality of them? And how have things changed over time? These are foundational remote sensing questions. And so sometimes it can feel like maybe you're not asking something novel or unique when you are going back to the same location, you're making the same measurements. And then when you go to the satellite data, hopefully you can put all of that information into this time perspective and recognize that, you know, sometimes what we're measuring, like a tree growing, happens slowly over time. That the 1,000-year-old plus General Sherman tree that Brian was talking about earlier, that grew slowly, right? And so if you were out there making measurements every single year about tree height and how much girth or growth that the tree has had, it might be really slow, right? It might be, you know, centimeters or maybe a meter or so at a time, but it may feel very unsatisfying. However, if we do that over a long enough period of time, we can start seeing these trends. And that is what Landsat has allowed us to do. It's taken a lot of technology, and now we have some new opportunities and new methods that are available to us. And part of that is actually, you know, using the GLOBE program. You know, continuing to add your observations into the GLOBE database will help us to use the satellite data in ways that maybe we hadn't really thought about before in the past. Or we can use what it looks like today to then use the satellite data to go back in time and ask and answer the question, how much has this area changed? So I want to really highlight all of the resources that are available under the land cover classification protocol. You know, this is the site definition that you should be doing before you do any GLOBE protocol, right? Even measuring pH in the water is a really important thing to define that site. Water changes, and Landsat allows us to actually see those changes over time, even if your students aren't able to get into that location more than that one time that they're making those measurements. So, you know, this ability to go between the field with GLOBE and be able to virtually go there with the satellite data is a really important skill and an opportunity that we can all do together to contribute to science and to help us to monitor the biosphere and do accuracy assessments of the maps that scientists are making. So I want to highlight this accuracy assessment tutorial is a really valuable way and maybe something that you might consider after you've made your tree height measurements or your land cover measurements. Compare it to some of the professional maps that are getting made. Do they work in your area? Do some change detection. And compare your location or what you're measuring today to what was there in the past. And I'll highlight a couple of the tools that we can use. But I really wanted to kind of take everybody back and recognize that the GLOBE program has been a big supporter of the Landsat satellite system and mission for a long time. And so we have a lot of resources related to this. Really, I think, important. Here I want to take you guys to the Landsat Science page that NASA runs. So this is a really unique satellite because it is not just managed by NASA. They are actually working with the U.S. Geological Survey, who have been the people who've been archiving the Landsat satellite images since 1975. And so there is this kind of multi-agency piece that has allowed this satellite mission to continue for 50 years. And so you'll see that there's some resources here off of NASA. And this is where you'll actually see on NASA TV is where the Landsat launch will be streamed through. So pay attention to that. It's going to be on Monday, 11/11. I think is the time on the West Coast here for those of us near California, because it's going to be launched from California, from the same place that all of the Landsat data satellites have been launched from. Again, a lot of really interesting stories are here that might really interest your students. There are some stories about scientists and how they are using this, ways that you can get at the data. That's one of the most important things, is they're not just the pretty pictures, but it's actually data that you can use. So there is a lot that is here, and importantly, I want to take you guys to this page that has a lot of resources that you can use in preparation to get excited, and hopefully as excited as I am right now about watching this newest observer go into space. But again, there are these activities that you can use to participate, to learn about the science, and to, again, think about what is your location on Earth going to be like in 5 years? And as this new observation platform is orbiting around Earth, what is it going to see? What kind of natural hazards or volcano explosions or different changes is it going to be able to observe in your particular location? So I think that these resources are very useful, and so I'll just let you guys explore some of those on your own. But I wanted to highlight that for the last 9 weeks, we've had this ability to participate in Camp Landsat. And this is really a useful set of resources around some themes. So again, Landsat has been monitoring Earth for 50 years. And so here we can actually see some of the changes that have been happening around the barren areas, non-vegetated rocks and rivers. How do those change? Importantly, thinking about and seeing how do the rivers impact the streamside trees and the riparian vegetation. We've been able to monitor and actually document meandering rivers, flood events, and those sort of changes that have been happening. These are great places to go explore and actually, do some globe measurements, and challenge your students to do some investigation around the changes that are happening there. I really wanted to highlight this week 4 Forests Forever resource, because that's what we're doing here, right? And importantly, again, this ability to look back at trees and how they are growing over time is only possible with the Landsat mission. There are some other satellite data that is available, like I mentioned, the MODIS one in particular, but ISAT-2 only has a couple years of data, and it's not going to continue collecting at the same rate as Landsat. And in fact, actually, to do a global estimate of tree height, we have to combine Landsat data together with that LiDAR data that's there. So, because this data is getting collected every 16 days right now across the globe, we have this ability to time travel, which I think is really cool. And so you can see that there are some videos here, and some other opportunities like this that you can actually do to try out some puzzles related to trees and what they look like in space, from space, the rivers around them, and some of those different features. And so there are a lot of these really interesting stories that are here. And so I just kind of wanted to highlight this as great resources for you to get in and even do things like crafts with these satellite data, right? And the Earth as art piece of things. Again, starting to kind of work with the data. So those are a couple of resources that I think are really cool and useful for you. I want to highlight the NASA Eyes on Earth application. This is an app that allows you to actually stand right alongside the Landsat satellite and travel around and actually, see Earth right now and what is kind of happening there. And I think this can be really useful for students to get that satellite perspective of things. Okay. I've highlighted this one many, many, many times. It's one of my favorite because it works with the data and type of research that I do. So I have a strong affinity for it. But again, this change over time piece is a really important facet to quantifying the carbon cycle, to understanding where are the carbon sinks and where are the carbon sources in the landscape and how are those changing. So before you can monitor carbon on the landscape, we need to understand where is it, and this is where the globe carbon cycle is an extension of that land cover, right? So first you map out what's in that pixel. I see some trees, I see some ground, and that can help relate to these colors that we're measuring from space or that we're displaying. But it's important to recognize that structure, that 3D piece that GEDI and ISAT-2 is measuring is a really important component of the biomass of carbon, of how much carbon is in that location on Earth. And so, these are things that we're trying to monitor and we're trying to understand the systems, right? So not just what's in that location, but maybe how does the loss of trees in this location contribute to somebody having a home in another location? This relationship between forests and human dwellings is interlinked, right? And so when you see deforestation in one place, where is that wood or timber going to? That's part of that system that we're trying to quantify. And Landsat is really what allows us to do that. So I want to highlight here that there are some nice resources that guide you through where to get actual data. And so I won't go through these right here. There's a lot of places to find Landsat data. So one of the things that I want everybody here to be cautious about is citing the source of where you get the data. Not all Landsat data is the same. And so if you want to do some measurements, you need to go to the source data and get the actual data. Be a little leery if you just go to a website and download a Landsat image. It may have been manipulated. It may have been transformed in some ways that may affect the actual pixel values or the measurements that were made. So this is a really important thing is we have Landsat viewers, and then we have the real raw data. And you want to be thinking about that key aspect. And the reason why I highlight this is because NASA Worldview is one of these places where you can go to explore the Landsat and now the Sentinel-2 data set together. This wasn't possible up until earlier this summer. And so if you go to NASA Worldview, you can start actually seeing the Landsat data right there. You don't have to download it. You don't have to worry about it. But remember, this is viewer data. You don't want to do analysis with this data. It might give you an indication that something is getting greener or getting less green. But remember, this is only viewer data. And so if you click on that harmonized Landsat Sentinel data set in that very first little piece, you can actually, you see that there are, there's a little viewer or guide that kind of walks you through, and it helps you to see some of the differences between the Landsat higher resolution data, 30-meter data, compared to some of the more coarse data, 250-meter data that we're used to seeing in the globe system or through NASA Worldview. So, Landsat 9 is basically the backup for Landsat 8. And so it's going to be very similar in terms of the information that's collected, how it's collected, and they will be very comparable. The key is that they will be in opposite orbits. So instead of having to wait 16 days for that satellite to come back over that location on Earth, we now only have to wait 8 days for Landsat 8 or Landsat 9 to go over your location on Earth. That timing is really important because we miss events. We miss green up, green down sometimes because of the cloud cover or when that satellite passes over. So, these are some trade-offs that we've had to make. It's really interesting to go through this guided tutorial here and start to kind of see the differences. You can actually compare the difference between the MODIS sensor and the 250-meter blurry images versus the higher resolution Landsat Sentinel data, right? And so, being able to go back and forth and see this spatial difference, I think, is really key with this. And so, again, you can kind of go through and it walks you through the scientific way that that NASA and the European Space Agency have figured out how to take 4 different instruments, essentially, and get them to work together so that if something is green in one satellite image, it stays kind of the same color green in the other satellite image. And so you see that we have 2 layers inside of here, one for Landsat 8 and one for that Sentinel. And so we can now go around almost anywhere in the world and you can see that what it looks like today, which I think is really, really neat. And I'll kind of highlight here, this is how they actually aligned them, really kind of interesting. But one of the keys here is the way that trying to get to it, the way that we can actually start to observe changes, right? And the ability to see things at a higher resolution, both temporally, spatially, and then also spectrally compared to what we on the ground are seeing. So I encourage you to explore that tool. I think it's really, really valuable. Another one that I'll kind of quickly highlight, because I've mentioned before, one of the things about worldview is it only shows you the world in natural color. And so we miss the opportunity to use that shortwave information that helps us to discriminate between grasses and trees, for instance. ESRI, a private company, that provides a lot of spatial technology, they have put together this Landsat viewer. This is really useful, and if you're thinking about putting together a story map or doing some spatial analysis, you might be able to take advantage of ESRI tools. They have a lot of the Landsat data already in their system, and so you might be able to take advantage of that. But regardless of whether you're going to do some of those things, you can always go to this website and you can start exploring a location. And you can go in and you can change the way that you actually look at the satellite data. So again, one of the things that you can kind of go through is start looking at what features on the ground and what they look like, right? And start looking at the different ways that we can put together these measurements that are made from space. And so, here I'm kind of zoomed out really far. We're not really seeing a lot of interesting things necessarily, but I'm going to, zoom in on a location that has some trees. This is, I think, one of those really important pieces. And, we can start to see the difference between the green vegetation. And again, I want to highlight how you can tell buildings with white roofs, buildings with black roofs, and just the way that the vegetation arranges with human development in this location. So again, a really powerful viewer that allows you to start seeing the landscape in some different ways. So globe, right? Globe is really important with this, and I think this is the powerful thing is remote sensing you can do before you go into the field. You can use it to identify where you actually want to observe, or you can use it after the fact to take that data and combine it together with your measurements, right? So there is an incredible a lot of data or ways that you can start using the globe data here together with the Landsat data. And I've highlighted some of those in the past, and so we have those on the Trees Around the Globe blog for sure. And so I just want to highlight that connection between the two that's there. I will end my little excitement here, I think, with two things. One is that Globe. One of the things that we're trying to do here with the Trees Around the Globe campaign is support global activities like monitoring the carbon in the on the landscape. And so there is a whole group of researchers and scientists and countries who are working together through this Global Forest Observations Initiative, GFOI. And they are trying to provide tool sets to everyone to actually track those trees in the landscape. And so, what we're doing here with our campaign and with what Globe has been doing for 25 years is fits in line with what everybody with what the scientific objectives have been since the beginning of the Landsat program. Again, where are the forests and where are the trees on Earth, and what is the quality of them, and how have they been changing over time? And so, there's these resources that are there. What we're doing fits into every community in the world. And we have some incredible tools that allow us to see those changes over time. And I've highlighted, this tool before, but I'm going to, take you to Portland, Oregon, where I'm currently located. And remind you, here's 1984 and, the natural color and kind of what it looks like in this area. I can just use this time slider bar to go back and forth and compare what's been happening and start to understand the landscape and the world around me through these satellite images and the satellite data that's there. And so I encourage you to make use of all of these resources. I've gone through a lot today because Landsat and this continuity mission that is hopefully going to be successful on Monday really facilitates global science, and science that allows us to not only look back in time, but hopefully, do some forecasting and make predictions about what the future landscapes might be or could be based on decisions that we're making right now. So very, very important, foundational to everything that we do. And, starting on Monday, hopefully we'll start getting new data coming in from this Landsat 9, starting about 100 days later. And so I expect and hope to see students starting to look at that data and doing new science, because nobody else will have looked at that information before. So great opportunities for people to get involved in our Trees Around the Globe campaign as we start thinking about these changes over time and trying to quantify them.
Thank you so much, Peter. If you could, Peter, also look at I think it's the most recent comment in the chat. If you could put that link in there for the one after Worldview. So yeah, thank you for that. And yeah, Landsat has such an amazingly rich, data, I don't want to say database, but amount of data looking at that change over time. And, some of the resources that Peter mentioned are, ideal for the campaign and for, getting your students involved, with everything from their own research project to submitting to IBSS and all of the above, and just learning more about our planet. So let me jump to a little discussion on ICET2 and GEDI. So, and then I will pass it over to Peter Falcon and then Dorian. But let me go ahead and share my screen again. All right. Sorry, I got a lot of things on this desktop. All right, let's start here. So I should also mention that, oh, well, there's a slide on there coming up. ICET2, sorry, got way too much going on here. All right. So lasers in space. We have GEDI, Global Ecosystem Dynamics Investigation. And that's on the International Space Station, and that measures, basically, you'll see here in a couple seconds, that measures tree canopy height in a particular area, particular latitudes. Then we have ICET2, the Ice Cloud and Land Elevation Satellite, which you all are probably familiar with by now, because we've talked about it frequently. But I wanted to let you know that on September 15, 2018, as you know, we started the campaign, but then also ICET2 launched. So ICET2 recently just celebrated its 3rd anniversary in space. So some of the graphic people created a little ICET2 logo here with a party hat, and the penguin you see on the left is our mascot called Paige the penguin, and on the right you just see the penguin stylized in the form of the number 2 with a party hat on. So I wanted to also let you know that in the 3 years that ICET2 has been in space, it has fired almost 1 trillion laser shots. And with each laser shot, you probably have heard before that each laser shot, there's approximately 300 trillion photons. And only about 12 of those photons actually make it back to the satellite, okay? But those ones that make it back to the satellite are super important. And with that 12 that make it back to the satellite, that allows us or affords us about 110,000 usable data points of height measurements from around the world every second. So that's why we have a ton of data with ICET2. And with all those laser shots, we have had approximately 2 billion tree height observations from ICET2 so far. And as you know, with ICET2, lots of things come into play. Since photons are light, it bounces off, gets reflected, refracted, absorbed, scattered, all those things. We have clouds to deal with, especially really thick clouds where the laser, the LiDAR can't penetrate. We have the cirrus clouds, which are made up of ice crystals, where we have a lot of refraction going on from the photons through the ice crystals in the clouds. So clouds aren't our number one friend with ICET2, but we deal with it. Lots of really smart engineers have written algorithms to figure out what we can do in these areas that are very cloudy, pretty frequently. But we need to get these height measurements. And I know with the campaign, we talked about ICET2 and trees, but as you know, since it's ICESat2, it's looking primarily, and its primary objective is looking at the height of the ice sheets in sea ice, Greenland and Antarctica, looking at glacial retreat, looking at actually snow height as well, but it also looks at the height of oceans and buildings and landforms in addition to the trees. So, happy 3rd anniversary from ICET2. And if you're a Twitter fan or a Facebook fan, you can go and look up NASA ICE, and we have a bunch of posts related to it. One thing I should mention that's really cool is that there was actually an old Zeppelin hangar in Germany that has been converted into a water park. And ICET2 flew over it, and it fired off, as it was firing off photons, one of it hit the pool in the water park, and it was able to measure the bathymetry of the pool. So if you go to the Facebook page, NASA ICE, you will see something called Photon Friday, and Friday is spelled PHRIDAY to go along with photon. You will see there, one of the scientists on ICET2, Dr. Kelly Brunt, highlights what she found with that you can actually see in the data that was actually able to measure the basically the bottom of the pool, that bathymetry in the pool in this small hangar. So that lets you know just how precise ICET2 can be. So I'm going to show you this quick video here. ICET2 elevates, the height of our planet.
From satellite data, we have a very good handle of how our Earth looks like. We can see oceans, we can see the sea ice, we can see our forest. What is much, much harder to measure is how high things are on a global scale, almost impossible.
ISAT-2 adds the third dimension, the elevation. Repeating measurements from ISAT-2 will allow us to measure changes in the ice sheets or in the ocean or in land.
ISAT-2 is designed to measure the changes that are going on in the cryosphere, in the polar regions.
All the change is at the edges. Those are the steeply sloping parts of the glacier that interact with the ocean, and that's where all the action is. That's where all the mass is being lost.
In order to estimate the mass changes, we need to know the height of things. The mission ISAT-2 carries a single instrument. It's called ATLAS, the Advanced Topographic Laser Altimeter System.
ATLAS sends out small pulses of laser light 10,000 times a second. And by measuring precisely how long it takes that light to go from the spacecraft down to the Earth and back up to the spacecraft, allows us to figure out what the height of the surface is beneath ISAT-2.
We need to measure the time of flight of a single photon or a single laser pulse with a precision of a billionth of a second.
NASA engineers had to come up with entirely new ways of measuring time very precisely.
A billionth of a second translates to an elevation change precision of just a few centimeters. Climate change is amplified in the polar regions. ISAT-2 is designed to measure those areas and will help us to understand what's going on with our planet.
So what's exciting about that is that, the precision of ISAT-2 is, second to none when it comes to laser technology. Firing off 10,000 laser pulses per second, able to measure the top of tree canopies from 300 plus miles above the Earth's surface is, absolutely mind-blowing to me. And I've been at NASA, this is my 21st year. So it's absolutely mind-blowing to me. And I'm glad I'm a part of this mission. I'm glad you all are part of this mission and you want to learn always more about this mission. So as you can see, ISAT-2 measures everything here. But I wanted to showcase with this you, and then I have a couple other slides, and then we'll pass it over to Peter Falcon, is that, a lot of people ask us, how the heck do we actually count photons with ISAT-2? Because there's some really big object in our solar system that sends out a lot more green light at 532 nanometers, this green light, than the satellite does, and that would be our sun. So, how does ISAT-2 know that the photons that are bouncing off, like the ice or trees, how does it know, or how do we know that the photons that ISAT-2 sends out are the same ones returning back to the satellite? And this is a question I get when I talk to students all around the world, all around the globe. You may have that same question as well. So this is a really cool video with one of the engineers, and then we'll continue after that.
The ATLAS instrument on the ISAT-2 satellite measures elevation by timing the flight of laser light pulses that leave the satellite, bounce off the surface, and return to ATLAS. The speed of light is very fast, and so a regular stopwatch would give us too wide a range of time, a big margin of error. The timing has to be ultra precise, less than 1 billionth of a second, in order to measure the height of the surface within just a few centimeters.
I'm Phil Lors. I'm Deputy Instrument System Engineer on the ATLAS instrument on the ISAT-2 mission. Calculating the elevation of the ice is all about time of flight. It's time of flight of the photon from the laser down to the surface of the ice and back. So what we are doing is creating time tags of the transmit when the laser fires and time tags of the receipt of the photon. So it all starts with the transmitter. When the laser fires, it puts out billions and billions of photons. We pick off a little bit of that and we send it to a detector and we produce a start pulse. And that is the start of our timing system. The spacecraft sends us a position and attitude message every second that tells us where we are in the orbit. From that, we calculate where we think the spots are on the ground. We have a rough database of the whole Earth with elevation as it travels up and down mountains and down into valleys and over ice sheets. For each spot, we calculate where we think the surface is, and we open up a range window. For every photon that's received in that range window, we produce a time tag. Now, the sun produces a lot of green photons too. many more than our laser does. So our laser produces billions and billions of photons with every shot. If you add the noise in there, you won't be able to tell the sun's photons from the laser photons. So if you just took one shot, the one laser photon would be lost in the noise. But if you take 200 shots, now finally you have enough surface signal coming out of the noise that flight software on board can pick out this is noise and this is the signal from the surface. Once we downlink the photon time tags from the receiver and the transmitter, and we have the range windows, we put those all together, you have the transmit time tags, you have the time until the range window opened, you have the receive time tags in the range window. You calculate all that put together, gives you the time of flight of a photon, which ultimately gives you the distance between the spacecraft and the ground. So if you know where the spacecraft is, you know the time of flight, you know the distance to the ground, now you have the elevation of the ice.
Technology that can measure elevation adds a third dimension to how we map our Earth and allows us to study change across the poles and beyond.
So I hope that helped out a little bit, a little bit of a, deeper understanding of, how the actual satellite works and how the LiDAR works on that. And, of course, he did have a focus on ice, but, that same concept works for tree heights as well, with ICET2. The same thing happens, they fire off that, condensed beam of photons, and that's what returns to the satellite, in that same beam. And, everything is time tagged. It's time tagged when it leaves the satellite, when it hits, when it hits the ground surface or a tree or the ice, and then back to the satellite again. So, with ICET2, we have this thing called open altimetry, which a lot of you have used before. And this is a way for us to see, basically where ICET2 has hit across the planet, meaning where are there, photons, where are the photons hit and what did it measure? And, for instance, here, this is just showing you, this is a school I work with in my area called James M. Bennett High School in Salisbury, where, we went out to take tree height measurements, and we found that ICET2, took some measurements right there at the schoolyard. So, and then we did some comparisons between, the data that the teachers took during a training session this summer with what ICET2 saw. And then you can do that, many different ways. There's a lot of things going on here. And please, contact me. I'll put my email in the chat in a second. But please contact me if you want to learn more about how to do this, looking at open altimetry. But what I did here is I did a comparison between, what's called the weak beam and the strong beam of ICET2. ICET2 fires off basically this single laser, this laser pulse. This laser pulse gets split into 3 beams, and each beam gets split into a pair. And a pair is a weak beam and a strong beam. And what I did was I found that in my neighborhood, one on my property and one across the street, the strong beam was on my property, basically the photon, and then the weak beam photon was across the street and on the neighbor's property. So I got permission from the neighbor, and I went over and took a tree height measurement, where this was located. And I did a comparison. As you can see here in the yellow, the ICET2 tree height, the ICET2 said it was 21.36 meters. I did NASA Global Observer 18.93 meters, and there was a difference of 2.43 meters. And then I did the weak beam measurement. The ICET2 height said it was 17.78 meters. I measured it at 18.54 meters. So it was a difference of 0.76 meters. So pretty close in both cases. But this is the type of thing you can do. If you go and look in your area, if you go to open altimetry and plug in your latitude and longitude, you can be possibly able to find that ICET2 dropped a photon over trees near your area, near that location. And you can go out and take observations and do comparisons just like this. All right. So now we can switch over to, GEDI, which is an instrument on the International Space Station. Okay. And this instrument measures tree canopy heights. As you can see here, it's a little different than ICET2 because it's not its own satellite, but it is an instrument on board ISS. And what it does is it fires off these lasers, and it measures the tree canopy height, from space. So it doesn't fire as fast as ICET2. You can see it fires off 242 times per second, and it has a 25 meter footprint on the ground. ICET2 you might have seen is a 13 meter footprint. So, this one covers more area, but it doesn't fire as much. But with a combination of the information from GEDI and ISAT-2, we have a really, really rich data coming in from this. So approximately since it was launched, which was in December of 2018, up to the space station, there are, oops, sorry, it went the wrong way. We have, got to go back again, sorry, offset. We have, you know, about 20 billion laser shots that have come from GEDI. So, you know, a lot coming right now. So, and also you can go to Open Altimetry, and right now you can look up GEDI data for tree canopy height. Now it's got a little more sparse than ISAT-2 because of the amount of laser shots, but you can see the beams here cover a wider area, you know, wider swath. You know, but right now it's in beta stage on Open Altimetry, but you can take a look at it. But a combination of this data, as I mentioned, and ISAT-2 data really helps us to do comparisons with that ground-based data, okay? So I will go ahead and stop here, and I will pass it over to Peter Falcon.
Okay, thanks, Brian. Let me go ahead and share my screen. Where's my screen save button again? It's always covered with you know what? I don't see screen save, Brian. Oh wait, I do now. Green there. Hopefully you guys, you can see that okay?
Yep.
Perfect. Okay, let me get rid of this. Move that out of the way. Okay, so we're going to go ahead and stay on the International Space Station, much like the GEDI mission. Actually, before I begin, I was going to say that one of the things I really love about the Landsat suites of satellites is that this is one of the few suites of satellites that's actually older than me. So I really appreciate that. So as I mentioned, we're going to stay on the International Space Station with the ECOSTRESS project. And once again, thank you guys for attending today. Thank you for your attention. This has been a great 3-year ride, and we hope to continue that, our campaign, and continue that educational journey with you. So once again, thank you for always joining us. So ECOSTRESS is a great way to understand plant life, plants, forest, jungle area, and understand the water that plants give off. Let me see here. Come on, buttons work. Why do my buttons not work? Okay, we'll do that then. So before I begin, I just want to say thank you very much to a few people that helped to put this project together. Dr. Josh Fisher, the former science lead, Dr. Carrie Cossey-Nicholson, who is a current science lead for the mission, and of course, Dr. Simon Hook, who is the principal investigator of the ECOSTRESS mission. So I'd like to thank them because a lot of them gave me some feedback and slides for this presentation. So to give you a little bit of background about ECOSTRESS, ECOSTRESS is on board the International Space Station. It was launched out of the Cape. I realized when I was putting the slides together, I must have been hungry because I actually typed KFC and I realized that did not look right. So it was launched out of KSC, Kennedy Space Center, on June 29th in 2018. And it took about 3 days for it to catch up to the ISS, to Earth, to ISS. It has an instrument, it's called a multispectral thermal infrared radiometer. It has a 400-kilometer swath. And much like the GLOBE program, where we have lots of partners from different countries all working together, this really embodies that same spirit. So we have people from NASA who put the instrument together. SpaceX was a private company. We utilize their launch vehicle. The Canadian Space Agency, we use a robotic arm to basically put us together, much like Legos in space. And they basically passed us over to the Japanese Space Agency's robotic arm. And we were put on the Japanese module, the node outside this module. So really, it's an international joint collaboration to put this instrument in space. Since it's on board ISS, it's at a 51-degree inclination, meaning it can get data from the tip of South America to the top of Alaska. And it gives us great resolution with this instrument around that band. Now, the cost is $30 million. It's supposed to be a 12-month science operation, but it actually got extended very quickly. And although this is a lot of money, to be put on a free-flying spacecraft, it would be upwards between $4 to maybe $800 million. So this is a really good bang for US citizens' taxpayer dollars, a really good bang for their buck, so to speak. They're getting some great data at a fraction of the cost of what it would be to put something like this in space by itself. And here is, of course, an image of that launch. We always launch over the ocean, so in case something happens, it needs to be detonated. It happens over the ocean rather than a metropolitan area. So it's always launched out of either the Pacific Ocean or the Atlantic Ocean. And it's a great image that somebody put together. Like every mission, we have science questions and we have science objectives. For ECOSTRESS, it's no different. So some of these science questions are, how is the terrestrial biosphere responding to changes in water availability? How do changes in the diurnal vegetation water stress impact the global carbon cycle? And the last one, you can basically sum it up with water management. Can agriculture vulnerability be reduced through advanced monitoring of agricultural water consumption? So we just want to know how we can better utilize water management when we're working with our agricultural crops. And then our science objectives are identifying critical thresholds of water use and water stress in key climate sensitive biomes, much like tropical rainforest, boreal forest, things like that. So I'm not going to go over each one. We talked about the diurnal cycle with our science question as well. And then the consumption of use of global water, large scales as well. So this is a slide that basically sums up what ECOSTRESS does and how it does it and why it's important. And this slide was provided by Dr. Simon Hook. So I just thought I'll just plop it in there because there's no better way to say it or reinvent the wheel. So just put that in there. The first part, we talked about the science objectives, right? We kind of talked about that. And what I want you to do is focus in on the image on the left. So what we're seeing there, that gray image in the back there, that is a plant's stomata. So plants have pores on the underside of the plant leaf, much like our skin has pores. And what happens is those pores open up, CO2 comes in, and then we use photosynthesis to make nutrients, basically sugars, for the plant to help that plant grow and stay healthy. And because of that, water is expelled through those pores. And ECOSTRESS can actually measure the water that comes off of those pores. And of course, the exact opposite happens. If you don't have enough water or you have insufficient water, those pores will close to conserve the water that it does have. And that could lead to the plant being stressed and then dying. So now let's go ahead and look at the green and red line that's going up and down, okay? That is the path of ISS, the International Space Station. That's not one day, that's a couple overpasses. And you can see on the bottom there, there's a time, 6 a.m., 12 p.m., and 6 p.m. So green is symbolizing there's a lot of enough water, that plant is not stressed. Whereas red, the plant is starting to get stressed, those stomata are starting to close to conserve that water. And as you can expect, around the hottest period in the day, 1 o'clock, it's going to be very stressed. Whereas in the evening, it's going to open up again and be healthy. And we want to measure that plant behavior throughout the morning, afternoon, and evening because it does change throughout the day. Let me see here. So now that we kind of understand, the importance of ECOSTRESS and the importance of measuring the water that comes off of those pores, how do we go about showing that to the science community and to the layman? So if we move over to the next image, this is the standardized way of measuring water stress. Okay, this is what we use to quantify water stress. It's called the evaporative stress indicator. So I often joke, scientists, much like students, love to use color to symbolize different things. Okay, so in this case, areas that are red, you can see there are high water stress areas, meaning the plant is not getting enough water. Whereas areas that are green, it's low water stress, meaning that plant is healthy, getting plenty of water. And this is model data, August 2012, you can see there. So we can see throughout the USA, areas where the plants are highly stressed compared to areas where it's low stress. And I mentioned, it can change throughout the day. Now, to get data like this, we need a couple of things. We need high spatial resolution, meaning we really want to zoom in there as close as we can to get really good resolution. And when you're measuring the pores of these plants, you really need high spatial resolution. You need high temporal resolution as well, meaning the time between one measurement and the second measurement. So we want something where we can get a lot of different data points, a lot of different measurements in that time. Of course, you also want to measure the diurnal cycle. We want to understand how that plant behaves, not just at one point in the day, but throughout the day. And most instruments will see an object at the same time of day, for like 5, 10, 16 days at a time. But you get that one data point at that one exact time. And then we also want global coverage. So we have these things with multiple missions, but not all of them, give us just the data that we need. For example, Landsat gives us excellent spatial resolution. MODIS gives us really good temporal resolution. GOES-R is really good for getting us diurnal cycle as well. And then, of course, it gives us global as well. So with ECOSTRESS, we can kind of get a great high resolution from each one of those aspects. Because we're on board the International Space Station, we're at that inclination where we can get near global coverage. We don't get the poles, but that's fine because we really want to focus on the really good part of our planet where all the grass is and trees and whatnot. So this is ideal for us. And plus the ISS will go over, it has a repeat cycle about 3 to 5 days. So we can get really good temporal data as well. As I mentioned, evapotranspiration changes throughout the day. And of course, those plants are going to be most stressed during the hottest time of the day. Let's see here. What else did I have here? Yeah, and then also, much like humans, if humans don't have enough water, they start to overheat. They won't have their body won't function healthy, and then they die. The same thing will happen to plants. If they don't have enough water, they will start to overheat, and then they will start to die. And evapotranspiration is a key indicator in the health of these plants. And we can see this from space as it is occurring. Okay, so here's a quick definition of evapotranspiration. Basically, you have evaporation from the surface, from soils, we measure that, and you have transpiration from plants. Or as my colleague Josh mentioned, we measure the sweat of plants. So you put those together and we have evapotranspiration. And this is very important because it is a key indicator of a key climatic variable linking water cycle, energy cycle, and the carbon cycle. So if you see that little leaf there, as we talked about, it's going to expel water. That kind of goes with the water cycle. It takes energy for that plant to grow and be healthy. So that goes in and plays into the energy cycle. And of course, it's going to have that CO2 coming in as well. So that plays a part of the carbon cycle. So it plays a major role in each one of those cycles. And then when we talk about some of the things we really want to focus on is biodiversity of plant life, right? So evapotranspiration is the leading climatic predictor of biodiversity. So if there is a forest fire or a drought, we want to see which plants are going to be the most hardiest, the most resilient to these events. And we want to see how that's going to affect the plant lives that are maybe not as hardy or not as resilient. And then that's going to change the biodiversity of forests and jungle areas. So we want to measure that from space. In terms of irrigation, we really want to understand water management for our crops, right? Here, if a farmer overwaters or oversaturates his crops, probably not going to be a very good harvest. And then if he underwaters them, of course, you're going to have a drought and they're not going to grow. So it's important to understand water management, and evapotranspiration is a key indicator of that as well. And of course, flash droughts. If there's areas where there's not enough water, that's going to be very prone for possible fires in the future. So we want to measure that as well. Weather is a key critical indicator, right? With evapotranspiration, it's a driving force with weather patterns, cloud formations, convection, things like that. So people who measure weather also use evapotranspiration as well in their measurements. And of course, climate variability, right? All those play into facets of what's going on with our climate. So now that we talked about some of the major things that evapotranspiration can help us understand, how can we use that in our science and our studies? Well, here's an example of an image from Costa Rica. This is during a drought. So this area received 75% less rainfall than normal during this drought that occurred in February 15th of 2019. So once again, we can see areas that are very high stressed. You can see that in red. And then we can see areas that are low stressed in kind of like that aqua color. So we can measure that once again from about 250 miles in space off of the International Space Station. And of course, this may lead to areas that may be prone for forest fires as well. We can measure stress levels in mangrove forests as well. Here is an area in Southeast Asia. It's a World Heritage Site, and we can see, once again, red, high stress, green, low stress, healthy. And we can see that as it changes, not only throughout the days, but throughout the years as well. And then for me, I live in Los Angeles. If you're interested in urban heat island, we can see the albedo effect coming off of these concrete jungle where I basically live throughout the day. So we're measuring surface temperature variations in Los Angeles. And as you can expect, the hottest areas, which are going to be in red, are areas where there's a lot of asphalt. We have lots of freeways, airport, oil refineries, and parking lots. It's really, as I mentioned, a concrete jungle. And it changes throughout the day and evening, and we can see that from space. One of the neat things as well, when we talk about urban heat island, is this is a really cool project, and they are doing a cool pavement pilot project. So basically, there's some this pavement that they can put, a material they can put over the pavement that acts to cool the area, changing the reflectivity or the albedo of that asphalt. So the city of Los Angeles wanted to do a pilot project, and they used ECOSTRESS data to see just how this this material was being used. And what we found was not only was the street where the material was placed cooler, but the surrounding area was cooler as well. And one of the last images I'm going to just mention is this is really neat. This is basically, it's a nice little article that we put together called ECOSTRESS Measures Plants Waking Up from Space. I did not realize, but plants have an internal clock, much like we do, and they wake up at different times. So here, the images in red, you can see that plant is waking up at 7 a.m. The next one, green, it basically wakes up at 8 a.m. And then in blue, 9 a.m. And when they wake up, they basically start to get into gear, absorbing sunlight, converting carbon dioxide, photosynthesizing, and doing what they do. And as I looked at this image, I realized if I was a plant, I would be the 9 a.m. plant unless you poured coffee on me. Not a morning person. And the last slide here is some of the latest things that the science team is working on. There's quite a few, but a few things I do want to mention is in red. The first one, ECOSTRESS has been used to monitor post-fire recovery in pine forested regions that have experienced high severity fire or likely to see growth of post-fire shrublands instead of pine forest recovery. So when there's a fire, we're in there being able to see the regrowth of that forest. Once again, seeing the biodiversity of that forest and seeing what's going to be growing post-fire. And that's really where the science team or some of the science team members are focusing in on. And for me, as I mentioned, we talked about urban heat island, ECOSTRESS. The next one I'm going to just read off. Temperature data has been combined with socioeconomic data to identify areas with a population vulnerable to heat-related islands. This is outstanding for me to see because this, like as I mentioned, I grew up in Los Angeles. It is a urban concrete areas that do not have a lot of resources, tend to have less trees, less parks, less green space. And because of that, are usually much hotter than areas where there's much more resources, much more green space. And then the last one there's a positive correlation is observed between percentage of households below poverty level and ECOSTRESS surface temperature, showing a environmental inequality. And this inequality, it really hits hardest in communities of color have a consistent positive relationship with land surface temperature. So, the hotter the area is, especially for older people, it's really going to affect their health. And we're able to see this with ECOSTRESS. And that's something that we did not expect to see from space. So I just thought I would share that with you. And with that, I'm going to go ahead and turn it over back to Brian, and then hopefully over to Dorian. So thanks a lot, everyone. Oh, and once again, very quickly, websites. There's websites, grab the data, and for more detailed, much better presentation on ECOSTRESS, please check out NASA RSET. There's a great 1-hour presentation on not only the instrument, but how to go about using data in a very in a tutorial manner where you can basically use the data and do some research as well. Okay, so with that, I'm gonna turn it over to Brian. Thank you, guys.
Thank you, Peter. I really love that graphic on the plants waking up. That was really cool. I've never seen that one before. So thanks for teaching me something new today. That's awesome. Yeah,
you're welcome.
Yeah, and I'll throw that coffee on you when I see you next time if it's before 9 a.m. So, all right. Well, let me. I know we're over the hour and a half, but as you know, we always like to. We kind of do that, it's because we know we have a great group here, and we always want to cover so much information with you. So, with that said, I will pass it over to Dorian Janney, and she will be talking to you about the GPM mission, or Global Precipitation Measurement Mission. Take it away, Dorian.
That sounds good. Brian, are you seeing my screen now?
Not yet.
Not yet. Okay, give me a sec here then. Let's see what's up. I told it yes. Dum dum dum. Okay, come back. Share screen. Desktop 1, share. Allow Zoom. Okay, I guess I got to go to system preferences. Sorry about that, folks. 1 second here. Any luck yet?
No.
Preferences, okay. I did put the link for this in, let's try, there we go, Zoom, and later, hopefully that'll work. Let's see. Sorry, I should have done a test there. Let's see if that works now. Okay, maybe now. Share. How about now?
It's loading.
All right, great.
There we go. We got it.
Okay, cool, marvelous. So I hope that you feel the enthusiasm that those of us who are able to directly support these Earth observing satellites have about the data that we're able to collect and the ways in which we want to make these data available to you, and also share some ideas that we have for how you might take these data and these concepts and use them to interact with the audiences whom you work with. What we're looking at here is 7 days of precipitation data. The colors are showing us precipitation as they're falling from, or as it's falling from the clouds to the ground. And these are the measurements from the ground that have been collected over a week-long period by the Global Precipitation Measurement Mission. And this is just to kind of give you a feel for the patterns of precipitation, the ways in which the winds are moving, and even you can tell where your intense precipitation is by those reds. You can tell where your frozen precipitation is by the blues. All kinds of really, really neat data that we can get as we look at the GPM data. So, of course, there is a real strong correlation between precipitation and trees. I'm not going to click on all these things here in the story map, but I wanted to make these resources easily available for you to have in your teacher tool belt, so you can pull them out and use them as works best in your classroom setting. The first part of this story map tells about the GPM mission, and that's what this video does here. Gives a little bit of a kind of a fun play acting explanation for why we measure precipitation from space. Basically, the Global Precipitation Measurement Mission, there's what it looks like. It's about the size of a fire truck. It was launched in 2014. And so it has been able to work collaboratively with 9 other Earth observing satellites that are up in orbit but aren't specifically collecting precipitation data. And because those other satellites are collecting data and sharing it through our core processor, every 30 minutes, we get an updated observation, updated measurement of how much precipitation is falling around the Earth. So as you might imagine, there are all kinds of real world applications for these data. If you go to this link here, Precipitation Education, it will take you to our education focused site, and you can find a lot of different resources there. Of course, climate change is having a huge impact on precipitation. Those of you who perhaps live in the United States, if you're out in the West, you may be experiencing some really severe drought conditions. If you were, say, in New York City, you might have experienced some severe flooding. So we all can tell that in a variety of different ways through the interaction of our Earth spheres, climate is having an impact on lots of different systems, and particularly on precipitation. If you go to GPM and climate change, you'll learn more about how GPM data are being used to help us better understand precipitation's changing amounts. And here's a new video that we just released last month that talks about the impact of climate change on a variety of these different spheres, and talks about the ways in which NASA satellites are helping us to better understand these changes. Then if you come down, no, I said I'd talk about trees and water. So you can come to this part of the story map here. If you click on this link, it takes you to a scientific article that talks about on the average, how much water trees need. And I included this diagram that explains how trees use water. And then when you come a little further down, as Peter was talking about, but actually both Peters, we're talking about transpiration and then also evapotranspiration. So I have here a really nice new video that focuses on transpiration and that tree sweat and how we measure that from space. A little bit of information on, water molecules and how we can take those cohesive properties of water models to help us better understand these processes. So a little bit of the science behind that, a little of the science behind evapotranspiration, and you can go here to learn more about evapotranspiration. And then I wanted to finish up by coming back to the GLOBE program and share here. You can go to the precipitation protocol, which basically uses a rain gauge. I have one outside my house and I check it every morning. And I now that in the United States, we are able to put atmosphere data, and it's not just in the United States. Some countries can do it, some can't. But using the Globe Observer app, I am now able to put in my atmosphere data on a daily basis. So my rain gauge data is a big part of the data that is very important and useful. I will click on this link here to show you. A while back, I created some breadcrumbs to help those of you who are using or thinking about using the rain gauge and the precipitation protocol, how you could go through and have your students compare and contrast what they are finding in their rain gauge and then what we are finding with the Global Precipitation Measurement Mission. So there are some step-by-step directions. I'll see if this opens up, and if it doesn't, no worries, because you can access it very easily. But these directions go through and help you and your students to have all the steps that you need to be able to compare and contrast your information. It's just taken a while to load there. Your precipitation information with the GLOBE precipitation information. I also put on here how you can create a spreadsheet and copy and save the data that you'll get from the precipitation measurement mission, and then compare and contrast those data to the data that you're getting in your rain gauge. So just some kind of cool things that you could do with that if you so desired. And let me make sure that, gotta close that one, come back up here to this one. Close that, okay. So a couple of things that you could answer, a couple of investigative questions that you could consider answering by using the global precipitation measurement data and perhaps precipitation data you're collecting yourself, or if you don't have a rain gauge and that doesn't fit into your environment, you could go ahead and use the GPM data and then also local weather data. So one might be, how are precipitation monthly totals changing in my location? How might those changing precipitation patterns impact the kind of trees that grow in my location? How much water do the kind of trees in my yard or in our schoolyard need per month? A great way of getting some tree identification in there, doing some math, getting a better feel for how much precipitation is falling on a monthly basis at your location. How are temperatures and precipitation expected to change in my region for the next few decades? And what kinds of trees should we plant in order to adapt to climate change in my location? So those are just a few questions off the top of my mind that I thought would be fairly easy to have students work with, whether they were in an elementary environment all the way up through senior citizens could most certainly take those questions and gather data to better understand them. And I'm going to finish up with an activity called From Satellites to Your Backyard, where if you just want to get in there and give it a try, find out how much precipitation fell in your backyard over the past 20 years, just go ahead and go to this website here, go to this activity, and it will take you through the steps that you need to be able to find out exactly how much precipitation fell in your backyard for the past 20 years. So with that, I will stop sharing. And there you have it. And feel free with the link there, you'll have all those things that I shared with you and more.
Thank you so much, Dorian. Yeah, love story maps. I need to work on those more with my stuff as well, because it's such a great one to do, to take a look at. I'm also going to be sharing in the near future an email out to the listserv for everyone. Is that we are going to, well, not we, but another Globe group is going to be featuring, Globe region is going to be featuring Yasraj Patel and his Himalayan expedition, and he created an amazing story map. It's going to be on October 8th, and I'll send all that information when I send an email out. But it's going to be, I can't remember the exact time, but it's super early for, well, super late for us. I think it's like 1 a.m. in the morning for us.
Yeah, 1 p.m.
Manila time.
In India, right? So,
Yeah.
or actually in the Philippines. So yeah.
Yeah.
So it's like 1 a.m. Eastern time, but it will be recorded.
Yeah.
And he's a very dynamic, energetic, young engineer. So you'll definitely want to look at it.
Yep, I'll invite everyone to that. We actually got the invite sent. We're going to be sent from Desh Patel of, from Desh Bandhu of India, Globe India, and we're going to be sharing that on social media in the next in the couple coming weeks. So with all that said, thank you everyone for the presentations and all of you for hanging on. I'm going to throw up a couple poll questions right now. If you'd answer those, just simple things that we like to. For 3 years of the campaign, we'd like to just collect a couple answers here to some questions. So let me go ahead and pop up the first question here. All right, let's see. I'm thinking if anyone else is going to be heading to that. I'm just going to do a quick screenshot of that just so I have that info. I know Zoom probably saved it, but all right. See if I can get to the next one here. here are the, that's that. Let's see if it goes to that next one. Right, let's go to the next one. This is about IVSS projects. Do you plan on working with your students to develop Globe IVSS projects this school year? You have 3 choices: yes, no, or not sure. Let me hit launch here. There we go. All right, it's understandable. We have 67% saying not sure. Up 57. That's changed. All right. I'm going to as well. And that one, I'm going to share those results. Here's what we see from that. So a little more. I like that. There's no selection, which is great. All right, and let me go to the last question here. And this is going to be, what protocols do you plan to have your students focus on for Globe IVSS projects? If you plan on doing that, you know, biometry, tree height, land cover, greenings, carbon cycle. Looks like we have some selection for all coming in. All right, wait a couple seconds here to finish that up. Just want to thank you for participating in this poll. All right, here we go. Looks like everyone is going to be including tree height, so that's awesome. So that's great. Large amount with land cover, greenings, and carbon cycle. So excellent. You know, thank you for that. Now, we want to end up. We know we're well over time, but as you know, and as I said before, we're kind of known for that, for doing that. But what I want to mention to you is, and maybe Peter Nelson can pop in for this, because I believe it was, you know, when we had our campaign team meeting, is that we came up with a question, you know, basically, do you think like a tree? Basically, what does it mean to think like a tree? Okay, I don't know, Peter, do you want to expand upon this a little bit? Because I know this is something that, you know, you think about, you know, when you talk about like witness trees and things of that nature as well. So, you know, maybe let's get the ball rolling on that in the few minutes we have remaining here, and take it away.
Yeah, thanks for that, Brian. This is, you know, sort of a little play off of another famous saying, which was by one of the former ecologist, Aldo Leopold, which was about thinking like a mountain. What I'm talking about like that is, how can we help our students? How can we help each other? How can we help, you know, the global community think a little bit longer term about what it is that we're doing here on Earth, or what is kind of, you know, our unique time, right? And so here, you know, this is one of the great things about the GLOBE program, right? Is you can actually go and explore other areas. Here's what Brian actually took of the General Sherman tree, right? And so to me, this exemplifies this idea of long-term thinking, right? You know, the fact that we actually still have these sequoia trees is because people before us made conscious choices to preserve those and not use them for themselves. That's the idea of kind of long-term thinking that we need right now, right? Not just thinking about our own generational or needs that we have right now, but actually trying to think long-term. The reason why we have these giant trees and that we're fortunate enough to have that is because of the carbon cycle, and in part because of the choices that people before us have made. So when we want to think like a tree, we're thinking about the air around us. We're thinking about the sunlight that's around us. We're talking about the water that's around us, right? And all of these things are really important to thinking like a tree and thinking about the resources that are there that allows us to have ecosystems that are thousands of years old like this. So I encourage you all to, when you're out there looking and making some observations or thinking about the environment that you're in, think about the trees. These are long-term living things in your landscapes that have witnessed, as Brian said, witnessed a lot of events, and some of those events have actually shaped the tree structure. The size of the crown, the shape of it, the fact that it's in that location. So I really encourage everyone to, think like a tree and think long-term. And what is that world around that individual tree that you're making that height measurement right now? What is that tree going to experience over the next 5, 10, 100 years? Be thoughtful about this. It's really important for all of us, to be thinking long-term like that, because the resources that we have available to us were because of choices that others made before us. And so we have that same responsibility to steward these resources and trees and not allow them to burn up, for a variety of reasons. And I'll say, to this point, part of the reason why we have the resources we do today is because people made choices in the past to sacrifice some areas because we need timber or trees to have homes or to have livelihoods. But we save some things like the giant sequoia trees in these locations to help those processes of earth continue on. And so, this is a wonderful and a really important concept that I encourage you to cultivate and to think about not only what you're experiencing in this world, but what these trees that we are focused on have been experiencing. So thanks for letting me end on that note, Brian. Think like a tree. What have those trees experienced and witnessed, and what are they going to experience?
I'm just thinking right now what those poor trees are thinking in the Sequoia Park, looking and seeing the flames from a distance, well, not even a distance, really close up now. So, and
Yeah.
as Bo mentioned, they're blessed the aluminum wrappers. And that's what they're covering a lot of the trees with, the base of the trees to protect them from the fire.
Yep. Not to mention, as you see here, the really thick bark that has evolved over time, because these trees have experienced a certain environment, water coming at certain times of the year, and over thousands of years, they have developed this particular way of dealing with fire. So it's not the first time that they've experienced fire, but it may be the first time that they've experienced fire in this particular way. And, they're clearly under as much stress as many of us are feeling right now. So I appreciate that. And I really look forward to seeing the photos and the ideas and the observations coming in about the trees around the globe this year.
All right. Thank you, Peter. Does anyone else have anything they'd like to discuss in the few remaining minutes? Well, additional remaining minutes. But we thank everyone for, staying on, as long as you have. That's great. We understand, everyone's time is valuable. And, and this also shows us, how important this campaign and trees and land cover and all these things are to you and your students and, everyone around you. So, thank you all so much for that. And, feel free to contact any of us if you have any more specific questions about, the missions, whether it's Landsat, GPM, ICESat-2, GEDI, ECOSTRESS, please contact us directly. Or if you want to learn a little bit more about how to do comparisons, remember on the website, there's also an area where we pulled out a lot of the tutorials that Peter and myself and some of the other folks have given, over the past 3 years. We pulled out those sections, they're usually, they average from 5 minutes to about 15 minutes. Maybe some might be 20 minutes. But yeah, so I'm looking at you, Peter. So 20 minutes or more. Yeah, because Peter, Peter is a fountain of knowledge with all this stuff. So, so take a look at that as well. And stay tuned for the recording. I've been getting emails during the webinar for people saying they apologize they couldn't make it. There are teachers who couldn't get their classes covered in time to join us. So they're excited about the recording of this webinar. So thank you everyone for joining us, staying on longer, and keep those fingers crossed. And I'll get to you. I'll send a message out as soon as I hear from the Global Implementation Office about the continuation of the campaign. And I'm assuming it should be any day now. So thank you all so much. Take care, be safe, and keep looking at those trees and looking at that land cover. So thank you all.